Hi, everybody. Today, our goal is to understand standard deviation and z-scoring by actually hand calculating them and then looking at them as a model so we better understand how they relate to data sets. So, we're going to be looking at two formulas today. This is the formula for standard deviation and also the formula for z-score. I'm going to hand write this down for you and go through it. They are actually fairly easy to calculate using a spreadsheet. Spreadsheets actually auto-calculate the standard deviation for you. Simple commands. These scores are individual scores related to data points, so those typically are hand calculated or formula calculated in a spreadsheet. Well, let's switch over to the paper and we'll take a look together. We're going to start with standard deviation. Standard deviation is the sum of the initial values minus the mean squared divided by n minus 1, all square rooted. So we got some different things there happening. So sigma, the Greek letter sigma means sum, add everything up. Chi initial is the value. Chi bar is the mean. And n are number of terms. So I'm going to take some AccuPlacer data. We'll be using this data several times in different applications. I'm going to take a small sample so we can do this simply, and we're going to put the chi I, or the initial values, down. So I'm going to write the initial values down that were individual student scores. Now, if we look at the first part of our formula, the formula says, I'm going to do this in stages. Some people would see this all in one shot, but I'm going to do it in stages just so you see how it all works. So then I'm going to take the chi initial minus the chi bar. Okay, so what is the chi bar? That's the mean. So the mean, or the chi bar, so it could be referred to as mean or chi bar. In this case, we add up all of these values. And then we divide because there are 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We divide by 10 and we get the mean, which is 25.50. Okay, I've pre-done that. So this is going, the chi initial minus the chi bar is 23 minus 25.5 and so on. And that equals, now let's take a look at these values. And just do some meaning making out of it because the calculations are not super critical. Anybody can do these calculations. But let's look at relationships because the relationships is what's really important. So if we know the average is 25.5, we know that these values are less than 25.5. So these are all going to have negative values on this side. They are less than the mean. If we look at any of the other ones here, 32, 44, they are larger than the mean, and so they get a positive. So now we've done basically this part of the formula here. Now we have to square the values. So squaring the values is that value to the power of 2 and or that value times itself. So I'm going to put those values in now too. Okay, there are those values. Don't be freaked out by this number here, 342.25. It's a big difference. This number is a long distance from the mean. So our guts are telling us maybe this is an outlier perhaps or something like that. But this is far from the mean, and this is very close to the mean, so that value is going to be small. And so now we've done the difference, then we've squared it. And now we have this sigma here. And this sigma is telling us to add all these values to this. We're going to take all these values and add all these values together. When we add them together, we get 482.50. So now we've got our numerator set, 482.50, and we're ready to go to the next step, which is the division portion. So standard deviation equals the square root of 482.50 divided by, there are 10 terms, so n, and it's going to be n minus 1, so this will be 9. Again, just the formula there. Sum, n minus 1, 10 terms, minus 1, equals 9. When we do that calculation, we get a value inside the parenthesis, inside the square root of 53.61. Take the square root of that value, and we get 7.32. So our standard deviation is 7.32. Great. So what? What does that mean? All right, let's take this apart a little bit. We'll conceptualize what this means. So let's see what this means. Let's draw a bell curve. At the top of the bell curve, we put the mean, and then at a certain distance out, we have the mean plus the standard deviation, and the mean minus the standard deviation. That's the first standard deviation. Then at another distance, we have the mean plus 2 times the standard deviation, and the mean minus 2 times the standard deviation. And finally, way out, I guess I didn't do a good job of blocking this out. The mean plus 3 times the standard deviation, the mean minus 3 times the standard deviation. So if you recall from the previous, if the mean plus the standard deviation is 25.5 plus 7.32, then we get a value of 32.82. That's the mean plus the standard deviation. Now let's subtract it the other way. 25.5 minus 7.32 gives us a value of 18.18. So we're saying 68% of the data is falling between 18.8 and 32.82. The second standard deviation, we just basically add another 7.32 to it, and that's 40.14. And then we subtract the other way, 10.86. Now remember, these are mathematical models based on the data that was provided. The smaller the data set, the more possibilities for irregularities or interesting things. And then here we have one more time for the third standard deviation, 47.47. And the negative is 3.53. All right, so there are those scores that are possible. This class average was a mean of 25.5. And then we have the deviations away from the mean. I'm just going to pop back in the original data just so we can take a look at it and do some more sense making out of it. So here is that original data, the original scores with the mean here, right? So if we look at this initial value of 23.3, 23, I'm sorry, that's about right here. And 21, that's about here. 22 is here, and 21 is here. 23 is here. 32, oh, it's right here, but it's still inside the deviation line. 44, that's out here. 22, 26, 21. So the way our data spread out, actually, we can see it's not a perfect. We have some data over here spread out more, a little concentrated here. So if we actually redrew this, this is what the normal curve looks like. If we estimated what the curve looks like a little bit, I think we're going to see something that looks like this. The mean here, because the data is concentrated here and spread out more over here. So this has a skew to the right look to it. Okay. None of the data actually came into the space. Nothing went out beyond the third standard deviation. But anyway, that's what the standard deviation looks like and its relationship for a set of data. Now, the z-scores are basically standardizing these values and putting them on uh, a different scale, where the z represents the standard deviation. So if I put z-scores on the bottom here, this is a z-score of 0. This is a z-score of 1, a z-score of 2, a z-score of 3, -1, -2, -3. Just eyeballing this before we calculate anything out, I'm seeing two values are going to be between 0 and 1. One value is going to be greater than 2. And seven values are going to be between -1 and 0. That's what I think should happen from these calculations. So let's take a look and calculate z-scores. So the z-score formula is z equals the initial value minus the mean divided by the standard deviation. Now, if you recall from the last set of calculations we made, look back, that was the chi-initial minus the chi-bar, or the means. It's the same thing. So these are the values we're going to start with. Just going to skip a step instead of writing them all down. We've already done it once. Okay, so I put down the values here of the chi minus the mean and chi-bar, same definition. Now we're going to divide this by the standard deviation. The standard deviation hasn't changed. It was already calculated from the last set, which was 7.32. So chi initial 1 divided by the standard deviation. I'll just write that out so you can see one of them. Minus 2.50 divided by 7.32 equals -0.34. -4.50 divided by 7.32 equals -0.61, and so on. Okay, and there are all my z-scores calculated out. Let's see if my relationship thing that I talked about earlier plays out. So I said we should have 7 scores that were between 0 and -1. 2, 3, 4, 5, 6, 7, and there they are. And then there we have the one value, 2.53, which appears out here. Great, that looks good. Then we had the one that was really close to 1. Oh, it was close, 0.89, right up there. And the one that was close to the mean, 0.07. There it is. So these are the z-scores, or standard scores, that can be used to help interpret information. And you might say to yourself, well, what is a z-score good for or used for? Let me give you a very practical example of what z-scores might be used for. So I'm going to share with you a really great practitioner's book that came out, I don't know, 7 or 8 years ago. It was called PLC Plus, Better Decisions and Greater Impact by Design. And it examined the idea that PLCs could be more productive if we looked at data in a reasonable way. And there are basically two things you want to happen in education. You want growth, students get better over time. And you want students to be able to achieve, perform at a high level. So growth and achievement are different things from one another. Growth is about, you might be low and you continue to be low, but you grew, so you got better. Achievement is you're achieving at a high level. So let's take a peek at what the model suggests. So students can be high achieving or they can be low achieving. They could have high growth or they could have low growth. So here's the first quadrant: high achievement and high progress. The goal of education, right? Have kids up here. Here's the one that's most problematic: low achievement and low progress, so low growth. So low achievement, it's just making low growth. And then over here, we have low achievement, but high progress. This one's not so terrible, in my opinion. Students might not be achieving well, but they're making good progress. This one to me is more problematic. High achieving students that make no growth, they kind of just plateau and they don't go anyplace. So that's not the one I like. So uh, I collected data, and we'll use the sample reference for this, of students who took a pretest And then they took a process test. We were actually doing some claim evidence reasoning writing on it. And so we wanted to see what they look like over time. So like look at the A student. Very low score to start, but at the end had a very high score. Okay. So that's the pre-test and the post-test. And so what I did was I calculated growth and achievement by converting these scores to z-scores. And when I did it, I graded it out because I use this with teachers. And so they didn't need to see the actual calculations. They just needed to know it happened so you could look at your data. And then what I did was I made this graph, and you can see this graph here. It plotted the z-scores. So it plotted achievement on the y, growth on the X, and then you saw the little dot, and then I had to put the student's name on it. And so the beauty of this was like you could look at this and say, these students here are all high achieving, high growth. This is relative to the sample. That's how we determined it. Here are the students that are low achieving, low growth, which is a little more problematic. We only had one student here, the B student, in the low achieving but high growth. So that was good. And then these students here were high achievement, but low growth. So not showing progress over time. So started high, stayed high, where it was high and increased even more. Low and low, and then started low, but made good growth and progress. So there's just a layout of z-scores here and a visual representation to make good sense of a set of data where teachers could make informed decisions about what was going on. I want to show you one last calculation. This is a really simple one. Standard deviation can be easily calculated on a spreadsheet. It's in a simple command. As I previously discussed, you start throwing this with an equal sign. So we do equals STDEV, open our parentheses, and highlight the cells we wanted to calculate the standard deviation for. Boom, we get our standard deviation. Really simple formula to calculate and shows us that relationship from the mean. All right, thanks very much, and I hope this is helpful. I encourage you to try hand calculating this so you understand, you get a feel for exactly what it is. Follow the procedure in the video of what I've done, and you'll get a good sense of standard deviation and the z-score. Okay, thanks so much.